Right. Good evening, everyone, and welcome to another CAS webinar. Tonight we have space news from Roy Bryce. Then our main speaker for this evening is Lyn Smith, whose presentation is entitled The Red Sun. Our next webinar is on the 22nd of March, when our speaker will be Nicholas Booth, whose presentation is entitled Perseverance and Hope, Looking for Life on Mars. And it's now over to Roy for the space news.
Right, thank you. And as usual,
Right,
just give me a second or two to get the screen going. So hopefully you can see the screen now, Samantha. Thank you. Okay. So you might have noticed at the end of last meeting, I disappeared rather precipitously in a strange fashion. The title of that talk was, Why Are There No Green Stars? And I remembered that in the January Space News, I'd actually included a slide of a green star. I thought it would be fun to try and show that slide again, but when I tried to share my screen, my computer just went crazy on me. So I couldn't switch off my computer, because if I'd done that, then it would have killed the meeting dead for everybody else. So anyway, as you can tell, there are actually no green stars. This is just a false color image that came from the Spitzer X-ray telescope. There's been a lot of stuff about Mars, but I'm going to go back to the moon for the first talk part of this tonight. So infrastructure is going to be one of the biggest components of any permanent human settlement on the moon. NASA Artemis missions are focused directly on building up the facilities and processes necessary to support a moon base. ESA is also contributing both material and knowledge. Most recently, they made another step in their path to explore some lava tubes and caves in the subterranean lunar world. ESA recently started the third round of a series of studies that focus on exploring lunar caves. So somebody wants in, I'm just going to let him in. The current round of talks is called a Concurrent Design Facility, and its study builds on the work done in the two previous rounds of Cisnova studies. Originally encompassing 5 studies ranging from how to lower a probe into a cave to how to communicate with the probe and pilot once they're in there, ideas were elicited from the public as part of the Caves and Pangea programs. From the 5 original concepts in the first Cisnova studies, ESA whittled it down to 3 mission scenarios: one to find cave entrances, one to thoroughly study a cave entrance, and one to explore a lava tube using autonomous rovers. ESA then decided to further evaluate 2 mission concepts that focus exclusively on exploring a cave entrance, but combining aspects of all 3 original mission concepts. Understanding even the entrance of lunar caves can prove invaluable to understanding the resources that might be necessary or available in the subterranean world of the moon. It's also key to understanding the radiation protection afforded by the lunar regolith. That protection, depending on its efficacy, can prove to be a game changer when there's any potential permanent lunar base could be located. The first selected mission plan is one led. Kenny, can you mute yourself, please? The first selected mission plan is one led by the University of Würzburg. Somebody else is coughing. They've developed a spherical probe that can be lowered into a cave mouth by a crane attached to a rover. The probe itself is encased in a clear plastic shell and will contain a 3D LiDAR, an optical camera, and a dosimeter that will allow the probe to read radiation levels at the cave entrance. Wireless power and communication is the focus of the second mission plan, developed by the University of Oviedo in Spain. In its scenario, a charging head is attached to the end of a rover-based crane which is then used to power and directly communicate with autonomous rovers that do not have their own internal power source. Power for the rover and charging head will come directly from solar panels connected to the rover. Mission duration for these experiments will be planned for 1 lunar day, or approximately 14 Earth days. ESA plans to link the mission outcomes of these two projects directly to two of their concerted lunar exploration efforts. Sorry, there's noises in the background that put me off slightly.
Who's in charge of muting? Can somebody else mute the unmuted people, please?
Right. Both these mission outlines are still conceptual at this stage, and neither has received full funding for anyone close to planning a fully fledged mission. However, it is clear that the ESA's stepwise process is providing value even before any mission is launched. The concepts that have resulted from it are novel and potentially executable with enough willpower and funding. Missions that have made it this far in the process do indeed stand a good chance of eventually becoming reality and contributing to our efforts to permanently colonize the moon. A recent study provides critical clues in the possible origin story for the two tiny moons of Mars, Deimos, and Phobos. Modern astronomy provides us with a snapshot, a look at the present state of affairs across the solar system. But what were things like in the distant past? The existence of the two tiny moons seen orbiting Mars presents a particular dilemma for astronomers. Close up, Phobos and Deimos resemble tiny misshapen captured asteroids. But how did they get into the neat tiny orbits that we see today? A new study conducted by the Institute of Geophysics in Zurich, the Physics Institute in the University of Zurich, and the United States Naval Observatory was published recently in Nature Astronomy. It tackles this problem with some intriguing results. The two moons of Mars were discovered by American astronomers Asaph Hall using the newly installed 26-inch refractor in the US Naval Observatory during the favorable opposition way back in August 1877. The very presence of the two moons has even sparked some outlandish theories over the years. Mathematically inclined theorists claimed that Mars should have two moons even before Hall's discovery, fitting the exponential cadence of Venus having no moons, Earth has one, and Jupiter has four, so they reckoned that Mars, sitting in the middle, should have two. This assertion famously turns up in Jonathan Swift's 1726 satire Gulliver's Travels. Though, of course, the discovery of Jupiter's fifth moon, Amalthea, in 1892, broke this kind of nifty pattern, tossing this coincidence into the footnote section of astronomical history. But Phobos and Deimos continued to capture controversy right on through the 20th century. Russian astronomer Joseph Slavkovsky even made the bizarre claim in 1958 that Phobos was an artificial space station, echoing an earlier deliberate April Fool's hoax perpetuated by astronomy popularizer Walter Scott Houston, claiming the same thing. The very first look at Phobos by Mariner 7 in 1969 and Deimos by Mariner 9 in 1971 revealed the truth. It was just a fairly prosaic looking pair of natural space rocks. 22-kilometre wide Phobos is certainly unique as moons go. It orbits Mars once every 7 hours and 39 minutes, just 6,000 kilometres above the red planet's surface, far closer than any other moon in the solar system versus its primary host. This also means that unlike Deimos and their own moon, Phobos orbits Mars faster than the planet rotates, meaning that viewed from the surface, it actually rises in the west and sets in the east. 12-kilometre wide Deimos is just above Mars's synchronous orbit and orbits Mars once every 30 hours and 20 minutes. Over the years, two competing scenarios have emerged to explain the existence of the pair of curious Martian moons. The first option is that they're captured asteroids. This isn't likely, however, from an orbital mechanics perspective, as such events are high energy and wouldn't produce the neat and tidy orbits with a low ellipticity and a low orbital inclination that we see today. The other option is that the moons formed along with Mars earlier on in the solar system's history, possibly from a single proto-moon or a giant impact on Mars, similar to the impactor proposed in the Theia hypothesis that formed Earth's large moon. Most moons are big, round objects, not small and irregularly shaped as Phobos and Deimos, said Amar Khan of the Zurich Institute of Geophysics. This is why the Martian moons were originally considered to be captured objects from the nearby asteroid belt. Yet, because of dynamical problems associated with captured objects, this scenario fell into disfavor, as a result of which in situ formation models were put forward. And obviously, the main reason that fell out is because it doesn't really explain why it's orbiting faster than the planet. Subtle aspects of the overall masses of the moon predict how their orbits will evolve. Tidal forces act on the moons over time, but the total energy of the system always remains constant overall, in accordance with the law of conservation of angular momentum. There exists a critical altitude, which is called the synchronous radius. Michael Afomsky of the US Naval Observatory said, if the moon is below the synchronous radius, the tides of the planet will drag the moon down. This is the case with Phobos. For Mars, the synchronous radius is at an altitude of 17,000 kilometers above the planet's surface. Phobos is well below this limit, and the tidal force of Mars lagging behind it and dragging it slowly downward. Deimos is above this limit, and the tidal force should lead the tiny moon, pushing it gently outwards from Mars. Deimos' outwards motion is a tiny 2 millimeters per year, slower than our own moon's 3.8 centimeters per year. Deimos probably won't escape from Mars in the lifespan of the solar system. The research team posed the question of what the Martian moon system might have looked like in the past, based on the snapshot we can see today. They developed a mathematical model of the propagation of the moon's orbits over time. Lead researcher on the study, Amar Bagari of EHT Zurich, carried out hundreds of numerical runs of the evolution of the planets and the orbits of Phobos and Deimos back into the far past. Is it really that certain that a body above the synchronous radius is doomed to fly away, and one below is doomed to fall back towards the planet? Says Fromsky, so I'm just letting somebody else in. Running back the clock in simulations, researchers realized that at some point in the past, Phobos and Deimos' orbit must have intersected. The study cites a period in time back around 1 to 2.7 billion years ago, when the moon's orbits would have crossed paths. The intersection of the orbit implies that the moons were born from a common progenitor, said Bagari. The parent body was most likely disrupted by an impactor within the time span mentioned earlier. The highly cratered surface of Mars indicates that the planet really was hit by many such objects. Of course, pinning this time down relies on knowing the precise composition of the moons in order to understand the effect that tidal forces will have on them over time. Now just some wee snippets to finish off. It's an interesting fact that Jupiter's Trojan region actually contains as many asteroids as the main asteroid belt. But it turns out that this region also has captured a comet. New images from the Hubble Space Telescope have revealed an object that fell into Jupiter's gravity well in just the right way that it was captured in the Trojan region. But it won't be around for long. Interactions with other objects and Jupiter itself will cause it to eventually drift back out again. And just a wee bit on Mars, with Perseverance firmly landed on the surface of Mars, the next step's to decide where the rover will go to study this ancient riverbed. In a set of images released by NASA and the US Geological Survey, you can see the pathway Perseverance is expected to take as it crawls up out of Jezero crater. There are exciting features along this journey, including possible shoreline deposits in ancient river deltas. Let's hope it finds some past evidence of life. Scientists recently discovered that the Earth's atmosphere could interact with the solar wind to create a giant swirling vortex in the upper atmosphere that rains down electrons instead of water, a space hurricane. The phenomenon was discovered in archival data captured by satellites back in 2014. The storm is believed to have been about 1,000 kilometers across, hovering several hundred kilometers above the Earth's North Pole, with several spiral arms, lasting about 8 hours before it broke down. Well, as always, thanks to the University Day people for the newsletter that gives me all the up-to-date information for this. And that's the space news for tonight. So back to Alice Amanda.
Right, thanks, Roy. That was really interesting.
Glad you enjoyed it. Thank you.
Yeah, because I hadn't heard about that. What you were talking about the end here, you know, in 2014 with that.
The space storm.
I hadn't heard of that.
There's a nice picture as well.
Aye, it's really had the wow factor. Yeah. And I mean, I'm behind with things right enough, but I hadn't seen the thing with Jupiter and, you know, and the comet getting captured. I hadn't seen that. I'm way behind with stuff.
I've tried to keep these as up to date as I can.
Aye. Right. So thanks again, Roy. That was really good. As usual. Right. So Lyn was fascinated by astronomy since the age of 7 years, when Sputnik went into Earth orbit and caused a world sensation. Yes, that long ago. She joined the British Astronomical Association in her early teens and got her first telescope, a rather cheap refractor that came with one of those eyepiece solar filters that Patrick Moore used to warn about. That went straight in the bin, as Patrick advised, and quite rightly so. Even at that early stage, the sun was the main astronomical body of interest for her. After that, life rather got in the way of observational astronomy, and it wasn't until she took early retirement at the end of the 90s that Lyn once again took to the telescope. The sun's splendor was waiting for her and didn't disappoint. During the very active solar maximum in the early 2000s, Lyn acquired her first hydrogen alpha telescope around this time, and that opened a whole new observing experience, recording filaments, prominences, and solar flares. Lyn became the director of the BAA Solar Section in 2006 and is still in the post, corresponding with members from around the globe. Her main duties are to coordinate monthly observations in white light, H-alpha and calcium K-line, produce a monthly newsletter reporting on solar activity, give advice and encouragement to new members or observers new to solar observing, to give talks to astronomical societies and BAA meetings, and to generally encourage and develop solar observing wherever possible. She also co-founded Clydesdale Astronomical Society in 2006 and was chairman of the society for the first 8 years. So let's give Lyn our usual warm Kaz welcome.
Thanks, Alice Amanda.
Right.
The intro's probably longer than the talk, I think. Right, I'll try and share this screen with some hopeful success. Yeah, that's it, cracked it. Right. That's it, we're there, good. Hopefully you can see that, because I can see it okay.
That's it, yeah.
Excellent, good. Okay, good evening. Yes, we're going to talk about the red sun. I've named that because we'll look at the solar atmosphere, or the chromosphere, tonight in a little bit of detail. So, right, okay, the chromosphere is quite a narrow band sitting between the photosphere and the corona. It's only about
Sorry,
2,000.
Lyn, could I just interrupt a second? We're actually, you've got your camera switched off. Are you wanting to do it that way, or?
No, it's not switched off. I mean, it is switched off, but there's a fault. I should have
Sorry,
said that.
okay, right,
Instance. Usually I appear on my iPad so you can see me, but on my laptop I've got to just put a photo up. It doesn't affect the PowerPoint, but it
Okay,
just
thanks
doesn't
a lot.
work. I've tried everything to get it to work. It won't work. So sorry, but anyway, just voice tonight. Okay, back to the chromosphere. It's about 2,000 kilometers thick and 10,000 degrees in temperature. So it's quite narrow. And we normally see it only during a solar eclipse, and it's just where you can see these prominences here, this little sort of red band around this eclipse sun. This other piece here is the corona, so we're looking at this little red band here just around there. Now we can see it anytime we want, of course, if we spend a small fortune and we get ourselves a H-alpha telescope, or we can adapt our own telescope with a blocking filter on the rear side here, which looks like a star diagonal, and a front etalon on there. This is the proper Coronado Solar Telescope. There's several types. There's Lunt and a few other makes. They're all fairly expensive. I don't know what they are these days, so around the 2,000 mark, up to about 10, I think, depending on what you want. Or this system you can put onto your own refractor. But again, it's pretty pricey, and I don't think there's a great deal of difference in the price of either system, so it's personal preference. This setup belongs to Dave Tyler, who is a particularly fantastic imager of planets and the sun. So you can see he's got rather nice equipment here, and he's afforded both, bless him. Right, so we can do that. We're looking, we see a red sun because we're looking at a narrow band. We're looking towards the red end of the spectrum through the 656.3 nanometer band. So that's all. We're emitting all other light other than that particular narrow wavelength, and it just so happens that the chromosphere shows up beautifully in that waveband. This is my own rather ancient telescope now. It's a 70mm Coronado, and I bought that in the early 2000s, about 2002-ish. And it was probably about a couple of grand then, which was expensive at the time. But when you think it's still going strong 20 years later, then it's not that expensive, really. You get some good use out of it. And every time the sun appears, I'm using it. So it's more than paid for itself, I would say. Right, well, the sun, we're looking here at, we have also the photosphere, which if you do any white light observing, that's what you're looking at. That's where you see sunspots and faculae. And then above that, we have the lower chromosphere and the upper chromosphere. And then we have, of course, this very, very hot corona out here. And it's still a bit of a mystery as to how that corona gets heated. So the photosphere is about 6,000 degrees, and then the lower chromosphere is cooler at 4, and then it goes up to 10,000 and then up to 1,000,000 degrees for the corona. So how does the corona get heated? Well, that is a mystery at the moment, and not too sure, but there's several theories. One of which is that there are vortices in the photosphere, and that these vortices generate magnetic tornadoes, and they spiral up into the chromosphere and then into the corona. And that rotation somehow creates magnetic waves that move along it and go into the corona and create heat. We still don't understand how that happens. There's also another theory, it may well be instead of, or maybe as well as, that there are lots of mini flares that are not bright enough to be illuminated. So you won't be viewing those mini flares in a telescope, but they're all over the sun, everywhere in the chromosphere, and that these somehow also generate or transferred this magnetic flaring generates heat up into the corona and somehow heats it up to this 1,000,000 degrees. As I say, it's not understood, and that's why we have a couple of missions currently on the way to the sun to try and throw some light onto the subject. One of them is the Parker Solar Probe mission. It was launched back in 2018, and it will complete its mission 2025, so it's a while, and hopefully we'll get some pretty good science back by the time it's completed its mission. So far, its latest perihelion, because it's doing umpteen slingshots and using Venus to slingshot itself in towards the sun, getting closer and closer and closer every slingshot. The latest perihelion was in January, and it's got to within 13.5 million kilometers of the sun. So that's pretty close, but it will get a lot closer. So at the end of 2024 and into 2025, orbits 22 and its final orbit 26, it will fly to within 3.8 million miles of the solar surface. So that is stunningly close. So it's going to touch the corona, hopefully sample the corona, and the results that we get back may throw hopefully some illumination onto how it manages to get to this 1 million degrees. So the probe itself is going to experience temperatures up to like 1377 degrees centigrade. So I hope it's well protected and doesn't melt, and we do get that information. And this is just a diagram just showing you how it's going to slingshot itself around Venus. And I've got a little movie, hopefully that works. Let's give you a better idea. This is Earth, and this is Venus, Mercury, and then it's busily slingshotting itself around umpteen times, as you can see, as the years tick away off on the left. 22, 23, 24, and finally 25. And that's it, mission completed. Meanwhile, we've also got the ESA Solar Orbiter, and that was launched 2020 in February. And that isn't going to go as close as the other one. It's going to try and sample the heliosphere. It's going to do some science in the heliosphere, which is the solar wind. So it's the solar winds is constantly coming out of the sun, as we'll see as the talk goes on. There's a low speed and a high speed solar wind. So it's going to try and sample that and just see how that's generated and find out a lot more science about that. It's also going to fly over the solar poles, which is something we've not viewed before. So we want to have a look at them and see how different they are to the bit that we normally see. So there should be lots of science getting done. And again, that will be operational between 2022 and 2027. So we may have to wait a few years, but I'm sure the wait will be well worth it. So it's already started its routine science. It's given us the closest images of the sun so far. As I said, it's going to look at the polar regions and measure the solar wind. Perhaps that will also throw some light on coronal heating as well. So these coronal holes then, if you look on the SOHO or on the Solar Dynamics Observatory website, then you'll see these images. They're all taken at various temperatures, and it's just these are very high degree temperatures, and that's why they're all different colors. They're looking at different wave bands because of the temperature that they're imaging in. And in this one, you can see all these dark patches here on the sun, and these are coronal holes that are showing up here within the corona. They tend to appear a lot around the polar regions, but you can get them anywhere in the sun. We're currently at solar minimum. We're just getting started now into solar cycle number 25. That's just getting underway. So things are still a little bit quiet, but you do tend to get a lot of coronal holes at this particular time. So solar minimum is better for coronal holes than maximum. So what are they? Well, these dark holes you can see in this picture at the top here. We've got one of the sort of central regions of the sun rather than the poles, which is quite interesting because of solar rotation. As the sun rotates quicker along the equator, the equatorial zones, so they tend to have these coronal holes. The speed of the stuff coming out of them is faster than it is at the poles, so that there's high energy particles coming out of these coronal holes at high speed when it's nearer the equator, because it's rotating faster, and that then has more chance of creating I think the word for it, when it impacts on the Earth's atmosphere, we get aurora. That's it, aurora, that's what I'm trying to think of. So what are they? Well, they're open magnetic field structures, and that's where the sun's energy or high energy particles are escaping from. So we have the high stream, the fast solar wind coming out of these coronal holes. As I said, they're more frequent during solar minimum, but they tend to be more prevalent at the solar poles. But it's those ones around the more equatorial regions that are more likely to cause the aurora because they're moving at a faster speed. So we have the normal slow wind speed coming out of the sun, and they're caused by the streamers in the corona, and then the high speed comes out of the coronal holes. Right, so let's move on to the chromosphere itself and do an examination in a bit more detail of all the features that you can observe there. I mean, normally people are looking at an H-alpha telescope, and what they look at is prominences and filaments. But your observing experience can be much enhanced if you look at the other features that you can also see within the corona. So let's just have a look at those in turn. And we'll start off with H-alpha plage. So there, H-alpha plage is that bright area there you can see around these sunspot groups. The bright patches, the areas of enhanced temperature, they're found mainly near to active regions, although plage can appear anywhere at sunspot latitudes. They often herald the emergence of an active region, and they can remain for some time after it's decayed. They are sort of similar to that of Faculae, which is a white light feature, but the relationship between H-alpha plage and white light Faculae is something, again, that's just not quite understood. Plage contains emerging magnetic flux tubes, and it has within it all these reconnecting magnetic field lines, which lead to release of energy and higher temperatures. Plage often surrounds sunspot groups in a sort of cloud-like formation, but as a sunspot grows, and if it's bipolar, which most sunspots tend to be, then the plage divides between the leader and the follower of the sunspots along the neutral line within the group, and that's where polarity reverses. Just look at this one. We see that most sunspots have a leader and a follower, not in all cases, but in most cases, because it's bipolar sunspot. So at some point we have, so say that was a positive sunspot, this would be a negative one. And you know that after 11 years, of course, that will flip around. The magnetism in the north is different to that in the south. And again, after 11 years, the magnetism flips around, so it reverses. So the sun comes back to its magnetic configuration every 22 years. But somewhere down the center of that group, there is the neutral line, which is interesting. So that connects the magnetic polarity of both those sunspots, and it's here that you can get shearing, and shearing is just a disconnection of a magnetic field and a reconnection, and that can cause tremendous bursts of energy and sometimes can result in solar flares. So in the neutral line of a sunspot is where to look for action. Basically, you often find dark filaments sitting over there, and dark filaments that erupt as well. A lot of features kind of sit over that neutral line. That's where the action in the sunspot tends to be. And you can see that clearly here. So there you've got your leader and your follower sunspot, and there you've got flaring activity right down that neutral line there. And that's where the neutral line is twisting and distorting, shearing, and of course releasing high energy when it reconnects. Right, there's something called spicules as well. These are jets of hot gas, and they're moving vertically at speeds of around about 50,000 kilometers per hour, but they're very short-lived, only around about 10 minutes or so. They're often larger at the solar polar regions, but they rarely protrude more than 10 arc seconds. And that's why in the BAA, you can't confuse them with a prominence, because that's also a sort of long arch, as we'll see in a while. But they are longer, prominences are longer than the 10 arc seconds. So if it's under 10 arc seconds, it's a spicule, and then for not reportable as a prominence. So prominences are only 10 arc seconds and more, and usually an awful lot more in height than that. So you can see these along the limb as an emission feature. This is a prominence here. This is a very large structure, but we're looking here along the limb at this sort of fringe appearance here. So these are all the spicules, and you'll find them all over the chromosphere. So they're all over the body of the sun, but seen as an emission feature here along the limb, and as an absorption feature here over the body of the sun. And in this one, you can see beautifully what I mean about them being over the over the sun itself. So you see all these sort of dark little mottling effects here. These are the spicules. And note in here, we have some stretching. I'll go on to that in the next one. But there's a different kind of pattern around the sunspot, because the sunspot is a very, very strong area of magnetism, and it's basically pulling all those spicules out of line. Right, so this image here shows you really very clearly got a fantastic filament down there, beautiful structure, but look at all those spicules. So you can see them all there all around there as an absorption feature. And again in this one too. So that's what it is. When you're looking at the sun, you see all this sort of mottling effect. That's what you're looking at, all these dancing spicules of plasma dancing about all over the sun. This filament, by the way, was absolutely enormous. You can't really see it from that image. You can't get the sort of perspective of it, but it was about 1/3 the diameter of the sun. So absolutely huge feature, which eventually lifted. Right, so what happens to spicules when they get entangled into magnetic field around sunspot groups? Well, they get stretched. Sunspot's area being so strong in magnetism that it stretches these spicules out, and they become, you can see them there, you can become elongated, they become darker, they can form whirlpools. If you look through an H-alpha telescope, you will look at a sunspot in H-alpha. You're looking over the top of it because you're looking at the atmosphere, and you'll see all these fibrils sketching out the magnetic field lines around that sunspot group. That's what you actually see. You see this, it's like a magnetic disturbance, a distortion. You can't miss it when you look at it. And that's what it is. You're looking at all these spicules being stretched, and that's what we call a fibril. And in this particular image, you can see them quite clearly. So there's your spicules, also a bit further out, and then the magnetic fields are starting to stretch them here. You can see them all distorting, getting thicker and turning around in this sort of swirling whirlpool fashion. And that image shows it, I think, particularly well. So they're around about 10,000 kilometers long, 2,000 kilometers thick, and you can really see the sort of magnetic signature of that particular group there. They do act as a medium to reunite the regions of opposing polarity. They can sit across the neutral line, linking the positive and the negative side, and kind of help to stabilize the group as it grows. These tend to be kind of young sunspots, developing sunspots, where you see these features growing. So talking about sunspots then, the sunspot is caused by sort of kinks in the magnetic field down in the convective zone. And as those kinks appear, they come up onto the photosphere as bright points of light, which we call filigree. But they're seen in the chromosphere a little bit differently. But these bright points of light, if they can clump together and become stronger and stronger in magnetism, what they do is they start to become strong enough to stop all that rising energy from the sun as it comes out onto the photosphere to be released. And then they stop down that rising energy, and so it becomes a darker area, a cooler area, slightly cooler, about 4,000 degrees as opposed to 6,000 degrees. And that is a proto sunspot. That's how they start. That's what a sunspot is. And then hopefully the magnetism will continue to increase and to grow. The sunspot will continue to develop, and we'll get something pretty spectacular. Doesn't always happen, of course. Sometimes they can just sort of emerge into a proto spot and then just die off and dissipate again. But that's what they happen. That's what we call an emerging flux region. And these flux tubes emerge out onto the photospheres, these bright points of light, and into the chromosphere as well, as these bright points of plage. That's how it appears in the chromosphere, as initial plage. And in this image, really, I think it gives you sort of a good idea how that gets started. So, as I was saying, bright points on the photosphere, and they become darker as they get larger and form a sunspot and appear as plage when we get into the chromosphere. Other associated things that we should look at in a moment are arch filaments and element bombs. And again, these are all associated with these emerging flux tubes, or these very early and developing sunspot groups. Right, so an arch filament, again, you can see them there. So there are sort of a larger and darker than a fibril, again sort of sitting across that neutral line connecting the two. Again, it's just part of the development. It is a fibril that has again grown and become even larger to what we call an arch filament. It's quite low lying and they're quite difficult to see. So observationally, these are quite difficult. But if you're an imager, then you can look out for these things. If you see them at the solar limb, you might see them as very low-lying kind of prominence, quite small. But again, they would be seen as an emission feature at the limb, an absorption feature over the disk. So they can be in straight lines, they can be curved. I say the bright emission at the limb. They're not that big and they don't last very long. Again, because this is an emerging and developing region, then they only last for about 30 minutes or so. Very good image there. You can see everything we've talked about. I mean, oh, this is a filament up here. It's quite a large one. Got your sunspot there, and you can see your spicules and your fibrils. They're etching out that magnetic signature, and then there's your arch filaments there. So the sort of still quite small, but there's just these low-lying sort of ribbons or lines right across that neutral line connecting the two. So again, just something else to look out for in your images. And have a rather nice movie here from Andy Devi, just showing all that feature going on again. So there we are, low line arch filaments across that. This is quite interesting. One of the observers of the section has been reporting these. He's called them transient solar bubbles. I thought at first they might be explained by the arch filaments we've just talked about being bright emission features, because these are very small, they're very low lying kind of bubble-like features that don't last long. They only last 10 minutes to half an hour. So they seem to fit in quite nicely with being arch filaments possibly seen at the limb. But then Roger says, well, actually, I'm seeing an awful lot of them at the poles. So that's sort of got rid of that theory. Because obviously if they were lying within the sunspot region, they're going to lie within the sunspot latitudes, and you're not going to find sunspots at the poles, because they tend to lie between usually about 0 to 40 degrees north and south, occasionally up to maybe as high as 70, although that's pretty rare, but you certainly won't be seeing them above that, and certainly they have never been seen at the poles. So this transient solar bubble, which I've got 1 or 2 members of the section now trying to image like mad, we're not too sure what that is. So that's a bit of a mystery. So again, this is sort of part of the fun really of solar observing and solar imaging, because you're finding stuff that you can't quite explain. So we've got some research to do, and would invite any professional, if they have a clue what that might be, please let us know, because we're not sure. Right, so I said about element bombs. Well, within an emerging flux region, or a very early sort of sunspot configuration, again, it's something you probably won't see visually unless you've got fabulous eyesight, which I haven't. But if you're imaging, you're more likely to see little bright points in these quite early sunspot groups, of course, in the chromosphere we're talking about. And these are mini flares. I mean, the mini, as far as the sun's concerned, certainly wouldn't be many of the occurred on Earth. They're, you know, still extremely strong events. But the small mini flares have this fantastic name of element bombs. But again, they only live for about 5 or 10 minutes, quite short-lived features. They can die out, and then after about half an hour or so, you might find that they re-emerge again. This is a bit of a close-up of them, what to look for. So just these little bright points in here. So you can either see them within sunspot groups, or if you look and you've got a dark filament across the sun, and you see some these bright points at the base of that filament, again, they could well be element bombs. And these features can cause that filament to erupt, and of course they can cause all sorts of goings on within sunspot groups as well. So they occur in emerging and developing active regions. They happen in the lower chromosphere, about 600 to 1100 kilometers above the surface. They are short-lived, but they re-emerge possibly a wee while later. And we see them commonly around the edges of sunspots or at the bases of spicules or active filaments. So if we move on to our prominence and filaments, which you're probably more familiar with anyway, these are sort of the normal things that people look for when they're looking at the sun's chromosphere. All we've got with the prominence, it's just we're looking at plasma which is caught in a magnetic field loop, basically. And a prominence is exactly the same thing as a filament. And this image here proves that it is the same thing. So you can see this feature starts here. It's dark over the solar surface, or so the solar atmosphere. So it's an absorption feature, and it comes out over the limb, and it brightens as an emission feature. So this is a filament, and this is a prominence. And because of that particular one is what we call a filaprom, took a lot of thinking up with that one, you can see it is the same feature curling across the sun and curling out and arching over the limb there. So there we are. That's a rather fine image of a nice prominence. So it's all this plasma caught in these field lines, and as the field lines evolve and move, so does the plasma. Some prominences can be quite quiescent, that is stable, and do not appear to move at all, maybe for a day, maybe all day, maybe throughout their entire existence. Others are active and can rapidly change, and in fact can even lift from the limb and disappear out into space in an eruption. When you're looking at an eruptive filament, then if you're looking at it through the telescope and you make a drawing, it's probably the best way. You don't actually see anything move in real time, but when you look away and do your drawing in detail and look back to the telescope, maybe a minute or two later, you will see feature changes. And if you do that over about an hour or so, you will see this feature change probably quite dramatically. And if you're lucky, you might see it lift and disperse into space. It really can be quite an exciting thing to actually watch, because it almost moves before your very eyes in real time. So they're about 10,000 degrees. They can be quite short. We've obviously seen the larger than spicules, but they can be a few tens of thousands kilometers long, or they can be hundreds of thousands of kilometers long. And this is half the beauty of solar observing, because you never quite know what you're going to see. So when you set up your telescope and put eye to telescope and look at the chromosphere, you might be fortunate enough to see one of these huge snaking prominences just snaking there off the limb and dispersing off into space. It's happened to me a few times, and it really is extremely exciting. It's fantastic. So prominences and filaments, they're not limited to the sunspot zones or areas. You can find them at the poles. You can find them all around the entire disk. Sometimes you will get several of them together. That is one single prominence, what we call a prominence half. If you get another prominence sitting with it, if it's within 5 degrees of the solar limb, it's all counted as one prominence. If the second prominence was more than 5, then you count them as 2 separate prominences. But sometimes these can be quite complex. You can get 3, 4, or 5 elements to one half, but you'll just count it as one prominence. If each of those elements is sitting within 5 degrees of the next, it just becomes the one feature. So as we've seen, they can be active, they can be quiescent, and they also form a variety of shapes, and that's quite a challenge when it comes to describing them. This is quite a common feature. It's a hedgerow, and as you can see there, it's also linked. There's lots of streamers, there's knots, there's all sorts going on there, but there's several strands to it. It's anchored more or less at each end, but with these sort of pillars in between. So you could call that, some people might describe that as an arch prominence, some as a hedgerow. It's really, there's no particular rule. You kind of describe it best you can. And here we have a pillar, or maybe a bent pillar. You see what I mean about that one being quite close to that. And so that would just be counted as one prominence, not as 2, it's a single half. And this one here, probably described as a flame, or if you're looking at the arch here, you might say, well, I think that's more like a double arch. Well, it's up to the observer really to describe it. This would be a pillar or a jet, possibly. This would be a loop. And some people may describe that as a fan, or even as a tree-like structure. So you just have to use your imagination. There's no set rules to it. Just describe it best you can. So when we have a solar flare, which is quite an energetic occurrence on the sun, then those can disturb filaments, they can disturb prominences, and they can cause those features to erupt. Escape velocity is 600 kilometers, I think, per hour from the sun. So if it doesn't reach that velocity, it'll fall back, and there are quite a few videos of that happening. But this one here, you can see this blob of plasma here being ejected by probably a flare, or some sort of motion within this has caused it to erupt. Perhaps one of the stems may come loose, and that may cause it to fling the plasma out into space. There's all sorts of reasons why these features become unstable and erupt. And there you can see a rather beautiful example of this particular prominence, which has become unstable. It's become unstuck at this end, and it's being flung out into space there, and the whole thing will detach and float off as a coronal mass ejection. This was a fantastic event back in 2010, I think it was, and we had this huge coronal mass ejection there, and that did erupt into space. And in fact, this made the very front of the BAA handbook, because it was such a stunning image of its time. And coronal mass ejection, so it's a violent eruption of plasma leaving the sun. So there's all sorts of high energy particles leave, but also actual plasma leaves in a coronal mass ejection. We have the central meridian down here, down the sun. And when you get a sunspot group coming around, or a nice filament, and it erupts, and that results in a coronal mass ejection, and it's in this sort of area, then that's going to result, hopefully, in a decent aurora, because that's coming directly towards the Earth. Anything appearing sort of around the limb or around this sort of area will go off into space, and it's unlikely it'll interact with Earth's magnetic field. But if you've got a nice large sunspot or something like that down here, then hopefully it will erupt, hopefully you'll get a flare, hopefully you'll get a CME, and hopefully we'll get an aurora. So let's look out for that. And that's just that eruption again, stunning image there of that coronal mass ejection. And another one a little bit later on as it left the sun. Beautiful. And he did a movie of a different one. It wasn't the same one, but then you can see what I mean here. It was anchored here. It's probably a little bit late in with that particular movie, but it was anchored here, and then something has caused that to erupt and to fling that prominence out in a coronal mass ejection out of the sun. Stunning piece of photography, actually. Now, once we've had a flare, we have something called post-flare loops that occur, and they're normally sitting in these quite distinctive loop-like contortions. But if there's a gap at the top here, if the loop isn't completely closed, then that leads to the plasma getting to the top, instead of looping round, starts to fall back to the sun. The sun draws it back down in what we call coronal rain. So that's just something else to look for. If you find this sort of strange looping type feature and this rain within it, then that's what you're looking at. You're looking at an event that has occurred after a solar flare, and it's causing this magnetic field line to form, and all this plasma, which is then rushing around the field lines. And say if there's a break in it, then it will fall back down as this coronal rain. The smashing image there of it as well. And you see another one there, and a little bit more developed there. And this video here of Alexandra Hart, that's just a rather stunning prominence, but you can see some of that. You can see that sort of prominence. Part of it there is trying to leave, trying to be ejected, but this part here is all sort of streaming down through the anchor points there and back onto the sun. You can see how the feature is suspended in that field line. It isn't really going anywhere. But here you're looking at a post-flare loop. You're looking at it edge on. So you're not seeing it to which you saw in the other photographs. You're seeing the edge on view, but just look at it. Look at that. Look at it coming down there. What a beautiful piece of video. She's captured that gorgeously. So we can have ascending prominences or descending prominences, and those are pretty much what they sound like. Ascending prominences or filaments are those that ascend, those that are caused to erupt in some forceful eruption, and they can end up as what we call a spray prominence. So that's something else you can be looking out for. If you see this kind of spurting spray going out into space, then what you're looking at is an erupting prominence as a spray type feature. Also, if you get a dark filament, a cracking filament there, that can lift as well. A variety of causes can cause these things to suddenly lift from the sun, and that's called a disparition brusque, when it's got several billion tons of plasma gets ejected from the sun in a CME. Another feature is called a surge. Again, it's something being caused by a solar flare, and it's a continuous expulsion of plasma, but it doesn't actually reach escape velocity, and it kind of falls back on itself into and causes sort of splashing effect, as you see within the chromosphere. So there you can see the jet. You can't quite see it falling back yet, but a surge can occur anywhere. It doesn't have to occur within a sunspot region. They can occur anywhere on the sun if you've got a flare, and quite often you find as flares occur at not within sunspot groups, but even at the solar limb, called a limb flare, and that's probably quite a good place to view these surges. So we've talked a fair bit about flares off and on, so let's have a bit of a closer look at them. So solar flares, they originate in the lower regions of the solar atmosphere. They're complex, they're caused by these sort of complex magnetic fields, untangling and reconnecting, so shearing. And all that stored energy is then released in large amounts, most of which is beyond the visible wavelengths. But occasionally, if you get a strong enough flare, then it can penetrate throughout all the wavelengths and actually be seen in white light. Now that's quite rare, but we'll talk about that in a wee moment or two, how to observe a white light flare. But most are a H-alpha feature. So they tend to occur about 2 years after sunspot maximum. And here we can see an M-class flare imaged by Andy Devi. So you can see the flare occurring in this very bright region here. And you can see that we've got some ejection. See that dark flash there? That's ejection of plasma coming out of the sun there. Now, and this is quite a different one. You've got more of a flash here. Rather than its sort of extensive area of flaring, but you can see this flash, and then you can also see that there's this dark ejection of material as well. But look at it, it goes out and it kind of falls back in again. It doesn't quite all of it disappear. We have an X-class flare, so this is a really strong flare. When you get X-class, that's one of the top class flares. So you can see this one bashing off here. I think we have a bit of an ejection of material as well, but just got to show how bright those X-class flares are, because people often ask, well, how do I know a flare when I see it? Well, really, you will, because you can't really miss it. It's so bright. You usually look at an area of plage, and then you see that bright area of plage brighten still further. Well, when it really starts to brighten, you can't miss it, and you know you've got the solar flare. Now, obviously, these videos are quickened up a bit. It's not going to happen quite as fast as that, but it will probably take place over sort of 10 minutes or so. Looking at the Solar Dynamics Observatory, that captured an X-class flare back in 2013. So you'll see the flash there. Again, it's speeded up a little bit, but look at the ejection there. You see the flash here? And then look at the ejection there. So there's the dark plasma being ejected from the sun. And of course, that's near our central meridian. So that could well have caused aurora. This flare, again, captured by Andy, is not around an active region. So it's not a sunspot group. It is actually around a filament. If you can make out the dark filament. And you can see it's on both sides of the filament. It's causing the filament to erupt. And this is called a ribbon flare. So we've got this sort of bright flaring region on either side of the filament occurring, or this sort of running river of bright material. And then it causes the filament to lift, and it tries to eject, but the sun's gravity is too strong and it doesn't have the velocity, and that brings it back down. So flares then, they tend to start quite small. They start with sort of this bright spots appearing within the plage, or bright plage, and then there's rapid growth over maybe half an hour or so, and to bright peak of the flare, which might just last a few minutes, and then slowly kind of diminish and fade away. So it decays a bit slower than it grows. So they usually associated with active regions, because that's where you've got the more potential for them to be with the magnetic field line shearing, but not always. And if you find a flare elsewhere on the sun than an active region flare, then we just call it a hider flare. So it's just another name for it. So again, we've just captured this flare here, so you can see how intense and how bright it is in this still. This is a flare back in 2014. I think that was an X-class flare, so one of the brightest that you can get. We had a sunspot in 2014, went across, white light object, which was absolutely stunning. I think I'll show you in a moment or two. And it released all these solar flares. I'll look at flare classification in a moment, but X-class is the highest. So you can see it just released one flare straight after another of the highest category, an absolute cracker. And that was it. That's what it looked like in white light. It's very contorted. When you see a sunspot like that, you know its field lines are going to be twisted. There's going to be lots of shearing going on, and there's lots of flares going to erupt, because it doesn't have the sort of classic follower and leader. You can see even in white light how twisted that is, how the magnetic field lines are looping around, causing all this distortion. It's almost like a solar hurricane. I mean, look, you've got all these bits of growth out here. You've got bits of penumbra, you've got little bits of umbra. So the umbra is the dark part in sunspot, the penumbra is the lighter part around it. But there's all sorts of bits and pieces sort of growing and fading. And again, that's when you've got magnetic field lines sort of forming, disconnecting, fading and twisting around. And that's where you're going to get lots of flaring going on. So that sunspot did not disappoint. That's where we got lots of X-class flares from. Interestingly enough, the Carrington sunspot of 1859, which was the famous white light flare sunspot, looked very similar to that in its construct. So if you ever see a sunspot going across the sun like that, then 24/7 get your solar hydrogen telescope on it, because you're going to get some action for sure. And here again, back to SDO, I think it was this picture. You can see a coronal mass ejection. We've got plasma being released into space in this huge explosion, basically. Fantastic photograph, that one. And that's what's happening. This is back to Soho. We've got the sun here. The sun is that size. This is the blocking coronagraph here, so we can't see the sun. But this is emerging from this region. Look at that. Huge explosion there, and that just gives you a beautiful example of how the plasma is disappearing into space. And when it's down the center line, that's what's coming earthbound. That's what interacts with the Earth's magnetic field, all that energy, high energy particles and plasma. The high energy particles hit it first, and 2 or 3 days later the plasma, because that's traveling at a slower speed, and that will hit again. So we should get multiple aurora over several nights when you get something like that happening. So what kind of sunspots then cause solar flares? Well, you want to be looking at D-class groups. We classify sunspots A, B, C, D, E, and F. A, it's just a very small single sunspot. But when you get up to D, you're looking at a bipolar sunspot, a leader and a follower, and probably all sorts of stuff in between. It's quite small. It's less than 10 degrees in longitude, as you can see some of these are. That's a sort of classic D type. If it starts to grow, which this has, and it becomes longer than 10 degrees, but not quite 15 degrees, it's E-class. If it reaches 15 degrees and more in longitude, and it's highly complex, it becomes F-class, the highest group. So it's D, E, and F-class groups that you're more likely to get solar flares from, because they've got the more advanced and tangled up magnetic fields associated with them. So we said about flare categories. There are 2 main methods. This is one, and this tends to be the older observers do this one, and the younger ones go more with the American satellite system that was developed more recent years. So a small one would be a subflare, or categories 1, 2, 3, and 4, 4 being the highest, and it's all measured in square degrees. And there are programs that you can find online, on information online, that can tell you how big a sunspot is in square degrees, so it's not difficult to find out that information. Another way of looking at it, it's the same kind of structure. and that's to do it in millions of solar hemisphere. And again, there are programs online that help you measure your images and tell you how many millions a sunspot is in solar hemisphere. But it's exactly the same. Importance would be 0 as a subflare, and 1, 2, 3, and 4. We also categorize it as a qualifier. It's either faint, or it's normal, or it's bright. So the faintest would be 0 and F. So 0F would be a subflare, but faint. And the brightest that you find would be, the importance would be 4 and brilliant. So a 4B would be the brightest. But more recognizable was the system devised with the GOES satellite, which the Americans devised. And we tend to use this more than anything, really. So we have 4 categories. Don't ask me why it's A, B, C, and then it just jumps to M and X. I've no idea, but it does. So these are quite small flares, and of course growing, and we'd get to C class, they become really interesting. But each group is subdivided into 9 categories. So we get C1 through to 9, then M1 through to M9, and each category is 10 times as strong as the predecessing one. When we get to X, that becomes open-ended. So we can get solar flares that are, X48, which I think we actually did. So medium to high category is an X, so medium ones are M class, but they're also extremely interesting. So like C class are good, M class are very good, X class phenomenal. So that's the way I sort of look at it. So X class, fabulous flares. I've not actually seen an X class. It is really luck, because they happen so quickly and without warning. There's no way of knowing when they're going to appear. It's just a matter of having eye to telescope at the right time, basically. We did have a X45 flare, which occurred in 2003. Initially, they thought it was only X28, which is big enough, to be honest. But because the particles flooded out the chip, they categorized it as X28. But later on their analysis, they realized that actually it was a lot stronger, and it was actually as strong as X45. So it's quite fantastic. If you remember back in 1989, there was a flare erupted and it hit Earth, and it knocked out all the sort of power grid in Canada on March 6, 1989. So that was, I don't know what that was in X-class terms, but it must have been pretty wick. The largest we have on record, the strongest X-class flare, was in 2001. Near the northwest limb, and it was out of an active region. And again, I don't know how far up the scale that went, but when you're getting into terms of X45, then they think that the Carrington flare was probably something around about that. So by deduction of that, this should have been visible in white light. So that was the flare. As you can see there, it's captured by SDO. It's a fantastically bright event. And that was the sunspot that caused it in white light. And you can see straight away how similar that looks to the solar hurricane that we looked just a few moments ago, and how similar that also is to the Carrington sunspot of 59 rather. Right, Hyder flares, we've mentioned them before. They are not associated, they're flares that occur not associated with sunspot groups. They tend to occur perhaps around a dark filament, something like that. They occur when the field lines twist around a filament, and as we've seen from that movie of Andy Davies, we have bright blobs start to form on either side of the filament, and then they become this sort of ribbon flare that we saw in Andy's movie. They tend not to be as bright as an active region flare, but they can be over a greater area, and again, I think you saw that in that movie. They were quite extensive. Another feature, and this is quite difficult, I mean, this is something only for images, and I think I've only seen 2 of these in the last God knows how many years, and it's called a Morton wave, and basically it's a shock wave from a solar flare, and you can see that appearing in the chromosphere. You can just about make it out there, around there, appearing. It is quite faint, and it's something you'll only capture with luck, with being an imager. So they tend to be associated with other sorts of features as post-flare loops. So if you see a post-flare loop, maybe look for a Morton wave. So that's the wave rippling out through the chromosphere from the flare center. The wave disrupts anything that it encounters, so it may well encounter a filament, it may well encounter a prominence and cause that feature to erupt. It can cause some filaments to blink out of visibility as the wave passes underneath them. It's called a winking filament, and I can only think what it does is to transfer energy from that wave into the filament, which then heats up the filament and makes it invisible because it makes it as hot as the rest of the background, so you're not seeing it as an absorption feature. Then as it cools quickly back to normality, you see it reappear as a dark filament. These are not easy features to find. And then sort of finally, really, to bring to a close, we look at white light flares. As I've said, these are so intense, so strong flares that they cross the entire spectrum and get into the visible spectrum. Now, we can see them, you know, really bright, but we're thinking there might be rare, let's say they're rare features, but maybe they're more common than we think, as long as they're only just on the cusp of visibility. So again, these are probably something for images rather than visual observers to look for. So sometimes if you get a really, really strong flare, you'll get this energy release in the corona. It releases that energy through the chromosphere. It'll travel straight down through the chromosphere. It'll travel into the photosphere. It will travel through and way down into the photosphere itself. And even the shock waves can reverberate right through the sun and come out at the other side. So these are really intense, energetic occurrences. Let's say the famous white light flare was by Richard Carrington back in 1859. They are very short-lived features. They are just more or less a flash, 5 to 10 minutes, and that's why we're not seeing so many of them, because it's really a matter of luck. You just happen to have your eye to the telescope at the time. So this is a white light feature. To see that flash in white light, well, fantastic. I've never seen one. Hopefully I might one day. Good luck hunting it. Probably something for images to look at, though. If you see some sort of bright objects in your image in white light, you could have a white light flare. There's also a feature called an umbral dot, not to be confused, which also looks like white dot in the photosphere. So you need to check online with the Gong satellite data, and if you can find an eruption, a solar flare listed at the same time as you see your white light feature associated with that active region, then you can confirm that, yeah, okay, I have seen a white light flare, but that would be the way to confirm it. This sunspot group back in 2015 did show a white light flare, so it did erupt as white light. That's not it, I must admit, but it did happen. Andy Devi, he managed to image this particular sunspot group as it went across. This is the following day. I'm not saying that was a white light flare, but you can see as it goes across on different days, it was flaring and flaring very, very brightly. So we've got a movie there. You can see a nice move. There's a dark filament there, a loop filament, which is associated with it, and the flare erupts it. There it goes. So again, a very nice movie captured there. And that's what the sunspot looked like. So it was an F-type sunspot, as we've seen. It was long, it was complex, it was mature, and that released a white light flare. So that's something to look for. So I think that ends my presentation tonight. It does. So I hope I've given you a better view of the chromosphere, and you know, to have a look for more features than just filaments and prominences. So I look forward to receiving your observations in due course. That's it. Thank you very much, and I'll answer some questions hopefully.
Clapping.
Yep, thanks, Lyn. That was really good.
Thank you. Trying to stop sharing, Lyn. That's it. Right. Okay, over to you.
Any questions?
Stunned.
Too much detail. There's a lot in there.
Yeah, there is. That's why I did this talk, because it's a bit more detailed than the usual sort of the top solar, you know, sort of looking at the solar features. It's for a bit more detailed look at it.
Mm.
With the solar flares, when they get ejected, is there any like significance with respect to aurora? I mean, is it make them more? Is it more powerful when it gets ejected?
Yeah, if you get actual material coming, get plasma coming out, then it is. I mean, obviously solar flares occur in all sorts of shapes and sizes like anything else. And the more powerful the solar flare, the more energetic the particles that are going to be discharged from the sun. So you're going to get a more intense solar flare. And then, of course, you'll get the plasma hitting probably about 2 to 3 days later. So you're going to get enhanced aurora then. So you get a series of aurora. Yeah, if you get something, say like the Carrington event that caused a white light flare, I think they experienced aurora all the way down to the Mediterranean. It's a pretty rare event. We're pretty lucky if we get aurora in Scotland, but to get it as far south as Mediterranean must have been quite some spectacular flare.
Mm-hmm.
Yes, John.
Lyn, you'll forgive me, as you know, I'm a professional astronomer.
Aye.
What's telling us about the physics of the sun? I mean, I can see from an observer's point of view, looking and categorizing all of these different things is interesting and fun, but are they telling us anything about the physics of what's happening in the solar atmosphere?
Well, as you know, I'm an amateur, so that's what I'm looking at from an observing point of view. I'm not a professional, and I'm certainly not a physicist, so I'm not the one to ask that question. We observe the sun, basically, for fun. That's what we do. We enjoy doing it. But yeah, I don't know how to answer that one, John. Really, I'm not a physicist. I can't really say.
Okay, well, fair enough. I mean, I don't have any criticism for just looking at the sun for the fun of it. I just wondered if there was anything fundamental that was coming out of it, but it's fine.
Yeah, I suppose not really. I mean, we're waiting for the professionals to come back with the data from satellites. That's probably the days of amateurs, doing a lot of discovery is probably over. We're over into the satellite age now, sadly. But
years ago, probably this is probably 1985 now, so that's how long ago it is. Somebody asked me at one of these kind of evening classes, why is the corona so much hotter than the photosphere? And it sounds like you still don't know the answer to that question.
No, they don't. No, they still don't know. They've got lots of theories and ideas, but hopefully these 2 probes that are on the way out there will give us some answers at last. We still don't know how it's heated to 1 million degrees. Still a mystery.
Yeah, quite. Yeah, well, I'm glad to know. I didn't know the answer then, and I'm glad to know I still.
Yeah, still don't.
I still don't know the answer.
We've got some at least more sophisticated theories, but we still have to prove them.
Okay.
Yeah, I guess it's ejector pushing out magnetic fields or something, and that's transporting the energy. But yeah, okay, fair enough.
Yeah, they just don't know how it.
Either. I'm an observational astronomer like you. I just use bigger telescopes. So,
yeah.
I mean, I want to know, is it big, is it round, is it green, is it rotating? But what that tells me about, I don't do cosmology, I do solar system stuff because I understand rocks.
Yeah. Yeah, it's just a talk really from the point of view, I suppose, really interests more solar observers than anything, because it just really takes solar observing a little bit further, to say, well, there are more features than just the prominences and filaments. So, I'm interested in your feedback. If you think it's too technical, tell me, because I say you're my guinea pigs. It's the first time I've given this one. So I won't be offended.
I have also a PST, and your talk was excellent, I've got to say. Yeah, you've really, really good.
Thank you, Claire. That's very kind. Thank you. Thank you, Wendy. Thumbs up.
Any other questions?
I don't think there's anything in the chat either. Okay, I've completely stunned you, I think. All right, then. Well, I have finished in time for you to go see Meghan and Harry's interview. So,
No, thank you.
No.
No.
No.